Okay, so let's continue from here. There's a few more things to mention about this sampling and reconstruction. After you have done the sampling and you have drawn the amplitude spectrum, let's say now you are going to filter the signal. Filter the amplitude spectrum with a low pass filter. Of gain 1. And bandwidth of 1/2 the sampling frequency. So in this case, if the sampling frequency was 200 Hertz, the sampling frequency was 200 Hertz. A sampling frequency of 200 Hertz. In radians per second, it is 400 pi radians per second. So for 1/2 Fs, which is 100 Hertz, that translates to 1/2 omegas of S, which is 200 pi radians per second. So this filter, this is a low pass filter. It is a gain 1. So usually filters do not attenuate the signal that is passing through them in their pass band, right? So they usually don't have, they are not amplifier, so they cannot amplify. So the gain is 1, ideally. So this is the cutoff frequency of this filter. Let me redraw this sampling scheme. We had a signal xt coming in, and it was sampled by PT, pulse train. And the output was xpt. Now this output is going to pass through this low pass filter, called this low pass filter, LPF. After going through this, so this is the amplitude spectrum. Before filtering, that is the So let me delete all these things that is cluttering the drawing. This is a signal that's going through the filter. So after filtering, so if this filter that's going to be having a cutoff frequency the cutoff frequency is plus minus 200 pi. 200 pi. Just looking at the positive side, negative side. I mean, I'm just without proper scaling, I'm just calling this the filter. Okay, I'm just filtering and taking out the signal inside this window. The signal, let's say it has an amplitude 1. So if it has an amplitude 1, then 1 times 400, right? 1 times 400 is also 400, right? 400. So filtering that out. Once you filter that out, the output is going to be okay. Let me delete everything that's outside this window. So that's what remains after filtering. Any questions?
No, sir.
Okay, then in that case, we'll move on to the next case and do the same filtering again. So again, I'm going to filter this. This is when the sampling frequency was at 300 hertz, which is omega's radians per second is 600 pi. So if I'm going to be filtering this with the sampling, with the filtering, with a cutoff frequency of 1/2 omegas of s, same thing as before, okay? So in this case, 1/2 600 pi is 300 pi, the cutoff frequency. Same filter, gain 1, Now the cutoff frequency is 300 pi, which is half the sampling frequency. So if you look, the 300 pi plus minus 300 pi somewhere here. This is what you can get. So drop a line here. Just assuming the filter is filtering this out somewhere around here. So magnitude of the filter is 1. It's not to scale. 300 times 1 is 300. So the output of the filter is not going to change in amplitude, but only the frequency, cutoff frequency. So this is the filtered output. Of course, 300. Minus 300 pi. Any question? Any question?
No, sir.
So you guys, if you look at this, and look at the original signal. So once you increase the sampling frequency, you get back you are able to filter out. You're not losing any bandwidth. You get the same bandwidth out. Once you increase the sampling frequency twice the bandwidth. Do you note that? This is a 300 pi, that's a bandwidth. So when your sampling frequency is 2 times the bandwidth, but our filter is half the sampling frequency. Now you can see you have recovered the sampled signal. But there's a problem. There may be a problem here. Right now, your sampling frequency in this case is 2 times the maximum. Remember, the bandwidth was 300 pi, right? Sampling frequency in this case is 600 pi. So when the sampling frequency is twice the bandwidth is determined by the highest frequency, which is 300 pi radians per second. You are able to recover the sampled output with full bandwidth. So that is a minimum criteria. This is an ideal filter. Let's say if this is not an ideal filter, let's say if this is not an ideal filter, it might look like this. So this is not an ideal filter. It might look like this. So you can see the filter has some, it's not completely cutting off what it wants. There's some spillover here. So it is going to include something, some distortion from outside the bandwidth. So that's the ideal filter. So it is best that when you filter, so therefore, in order to solve this problem, we have to increase the sampling frequency beyond 600 pi. So look at the next case. Here, your sampling frequency is 800 pi. Is it? It's greater than the minimum sampling frequency of 600 pi. So when your sampling frequency is 800 pi, so now you apply a filter here, same filter, same gain, 1/2 the sampling frequency, which is 400 pi. So the filter is going to be somewhere around here. The filtering. This is 400 pi minus 400 pi. Now the filtered output okay, now this is better, just in case this is not an ideal filter. If this is not an ideal filter, say it's doing this, but at least we have some space here. Can you see? We have some spacing here, which will be less prone to distortion. It's still outside here in this region, in this area, still there's no other signals that will be included, that will be passing through the filter. So it's much better if you're filtering, if you're sampling slightly bigger than the bandwidth, twice the bandwidth. The sampling frequency is more. Sampling frequency is more than the twice the maximum bandwidth, or the highest frequency is better. But however, if you're a designer, you'll be concerned about this, because the higher the sampling speed, that involves more hardware, complication, software. So you have to balance between optimum and what is really feasible. Okay, any questions?
Sir, why we getting 400 pi, sir?
400 pi, because half the sampling frequency, the sampling frequency for this case is 800 pi.
For the
The sampling frequency is 800 pi. So the filter cutoff frequency is 1/2 the sampling frequency. Filter cutoff frequency. This is the filter cutoff frequency.
But sir, another side is negative 300 pi, right?
Yeah.
The another side.
Yes. But you know,
No.
usually this is a mathematical thing. You know, real filter, we don't have negative. That's a different story. We want to talk about the negative, why there's negative. But really, the filter, in real world filter, there's only positive part, right?
Yes, sir.
It's only positive part. So this is a mathematical thing, the negative thing. But we don't have time. If we have time, I'll go through the theory and see why we're getting negative. Negative is mathematical thing. But really the filter, the low pass filter will look like this. 0. Because when you go to the network analyzer or spectrum analyzer, you only see positive frequency. So ideally, sorry, this is ideal. Okay. Ideally, it should look like this, isn't it? I mean, and there'll be a 3 dB cutoff frequency. The bandwidth is truly here. It won't even go to 400 pi. It'll be less than 400 pi. But we are just talking about ideal mathematical thing. The negative side, if I have time, maybe the next lecture I can go through why we have negative. But negative is mathematical thing. Just now somebody asked me the filter, because our filter cutoff frequency is 1/2 the sampling frequency. Our sampling frequency for this case is 800 pi. So 1/2 the sampling frequency is 400 pi. JJ, were you asking the question?
Yes, sir.
I mean, did I answer your question?
No, sir. My question is, there's a negative 300 pi, and the other side is 400 pi. So, I don't get
Oh,
it.
this one. This
Yes,
is
sir.
typo
Oh,
problem.
sir. Okay, sir.
Sorry about that. Sorry. Again, I'm writing. That's okay. Now is more correct. Thanks. Xt is e to the minus 2 . So there's a time delay. You can find the Fourier transform of this from the table, or you can find the Fourier transform of this. We can find from the table, or you can find it by integrating using the definition of Fourier transform. So guys, if you want to do this using the table of Fourier transform, then you find out what is the Fourier transform of negative t. You know, what is the Fourier transform of this? From the table, the Fourier transform of E, A, T, U, T, is 1 over A plus j omega. A plus j omega. Okay. So the Fourier transform of e to the minus 2t is two plus j omega. You time shift, then all the time shift is doing is just shifting the signal, right? See, if you look at the signal in the time domain, it is going to be looking like this. If you sketch the signal, it will be looking like this, e to the minus 2t, right, to ut. And then if it's time shifted, then it is shifted by 1 to the right. Okay. So it's time shifted. A time shift in time domain is e to the j omega. Two plus j omega. Okay, I can also show you how to integrate this. Magnitude of this is equals to the magnitude of e to the minus j omega divided by 2 plus j omega, which is equals to e to the minus j omega magnitude divided by 2 plus j omega. Go back to the basics, when you have an equation, the magnitude is real part squared plus imaginary part squared. It's all the magnitude. Using this concept, you should be able to find this. Minus j sine omega. The amplitude is cosine squared omega plus sine squared omega. So what's that equals to? 1, right? Then the magnitude 2 plus j omega is 2 squared plus omega squared, which is square root of 4 plus omega squared. Therefore, the magnitude is 1 over 4 plus omega squared. So that's the magnitude. Sketch the magnitude. I think you can sketch the magnitude.
Sir,
Yeah,
the square root part one, the square cos square omega, why become plus one? Is it should be minus?
minus is imaginary part. This is outside here, plus, minus, okay?
Oh, okay, sir. Understood it.
Okay. Anyway, you should ask question. No matter how simple it may be, 0.01 or something, you just choose a few points. You put a middle point here, and then maybe put a -1 or -2, -1, 1. 3 points is sufficient to sketch this. Okay, when you plug in -1 in that equation, omega squared is 1. 4 plus 1 is 5. So 1 over square root of 5. 0, and this one also 1 over square root of 5. So this is an even function. These are the points. When omega is 0, sorry, it's not 1, it's 1 over 4. 1 over square root of 4 is 1 over 2. So when it's 0, it's 1 over 2. So it's going to be like this, something. As long you get the, it's going to be something like this. You cannot go like this because this equation is never going to be 0 for any value of omega. Okay. Now, because this is in the numerator and this is the denominator, so since in the denominator you have to subtract, so you put minus sign there. Division, so when you convert them to phase, division becomes subtraction. Correct? Like for example, if you have 90 degrees, okay, and then divided by 2 at 45 degrees, how you do this? You go 6 divided by 2, and then you go 90 minus 45 degrees, right?
Bracket 10 over 2.
10 over 2.
Yeah, I don't get it. Why are we getting this?
10, oh, omega, yeah, omega, sorry. Omega over 2. This is what you cannot get.
Yes, sir.
Let's say you have an angle, right? Let's say you have, this is 3 and this is 4. So when you want to find this angle, how do you find it? Theta is tangent inverse 3 over 4. Okay. Like for this is, if this is imaginary axis, imaginary axis is vertical, the real axis is horizontal. So when you want to find the angle, it's always going to be vertical length divided by the horizontal length, tangent inverse of that. Okay, now you take your calculator, JJ, you take your calculator and find out what is tangent inverse of 0.75. 3 over 4 is how much? 0.75. Can you guys find out the tangent inverse of 0.75?
36.87, sir.
3 divided by 4 is 0.75. How much you said?
36.87, sir.
36.87 degrees. Okay. Now if you take this triangle and you put here, let me draw this bigger. Theta is 36.87. This is adjacent. Adjacent is cosine. Okay. What is this? Is the magnitude, right? 4 squared plus 3 squared is how much? 16 plus 9 is 5, isn't it? This is 5. Is that 5, guys?
Yes.
16 times. So now if I want to find the let's say if I want to find the horizontal length, it's going to be 5 cosine 36.87, right? Calculate that, please.
$3.9999.
So that's approximately 4, isn't it?
Yes.
So now you find this 5 cosine, 5 sine 36.87 degrees.
$3.0000.
So approximately 3. So this is geometry Pythagoras theorem. Pythagoras theorem. Pythagoras theorem is vertical whenever you want to find the angle. Okay, whenever you want to find the angle, theta is equals to this is y and then x is tangent inverse y over x. Okay, that's all I'm doing there. Okay, imaginary part. If you draw this for this part here, this is imaginary part. Imaginary part. There's a coordinate here. The coordinate here is 2 omega. That means the real part is 2. Imaginary part is omega. So this is forming a triangle. So in order to find this theta, is tangent inverse omega over 2. Do one more problem quickly. Of the sequence. Zero, zero is a discrete time. We have done this before for different equation. So the discrete time Fourier transform is given by this formula, n equals to minus infinity okay, but we only have signals that's going from, we have 0 signals here. The signal starts at -1, 0 and 1. After that we have no more signals. -1, -1 to 1. When n equals to -1, applying the n is equal to -1 to this formula, next n equals to 0, next n equals to 1. N equals to at -1, the amplitude is 1/2. So this is like these are the amplitudes, the value. Okay, this part here, 1/2, and this one minus minus becomes positive. At 0, the amplitude is 1. E to the power of 0 times j omega becomes 0. E to the power of 0 is also 1. Okay, so this is a 1. Factor out the 1/2 and combine the exponential part. Okay, so the magnitude of this this is quite easy to plot. Magnitude is just 1 plus cos omega. There's no imaginary part here. The real part is the magnitude. And the phase. This is mag and this is the phase. Phase. Whenever you are confused, you can always go to the basics. I know, because we told you last time, to find the magnitude, it's always imaginary part squared. There's no imaginary part here. 0 squared plus the real part squared. So that will give you this, right? Similarly, go back to the basics to find the phase. To find the phase is tangent inverse, a real part, sorry, imaginary part over real part. Imaginary part is 0. That's a real part. 0 over anything is 0. Tangent inverse of 0 is how much?
Zero, sir.
Okay, 0, thank you. We look at this. This is a cosine with a 1 DC offset. So this is 1 cosine. I just can roughly draw this, not need to be very accurate. Okay. After drawing, you delete this. This is 2. So this is not bad. It's easy to sketch. The previous one was nasty. Okay, guys.